Today we are going to take some important topic of J in the inorganic side. It's an coordination compound, and first, for studying coordination compound, we have to understand that what is coordination compound. In coordination compound, it's a complex salts only. First, simple salt is what? That any acid plus base, that it gives a simple salt plus water plus heat of neutralization. When two or more salts are allowed to chemically combine together in a fixed proportion by weight, then molecular addition compounds are formed depending upon their behavior. In aqueous solutions, they are classified into two, which is double salt and complex salt. So, molecular addition compound, when two or more salts take and combine together in a fixed proportion by weight. A molecular addition compound that are formed is only a complex salt or, or double salt. Depending upon their behavior in aqueous solution, they are classified. Double salts of what? Molecular addition compound in which individual compounds don't lose their identity in aqueous solution and give positive test of all constituents is called double salt. Okay, I am giving example. This is a definition, so don't be stuck on this. Okay, so I'm giving a definition. So first take example like ferrous sulfate FeSO4 is simple salt combined with another salt which is ammonium sulfate NH4 2CO4 SO4 plus water that we are taking in aqueous solution as it's a water. So taking a test tube, mix it, and we get more salt which is light green crystals, and it in in water it gives all the constituent ions that it will give Fe2 plus so NH4 minus, SO4 2 minus, and H2O. So it gives positive test of all constituent ions as they do not lose their identity. Its individual components like Fe2 plus do not lose their identity as they form double salt. While adding two salts, they form double salt, but their components like Fe2 plus and H4 minus they do not losing their identities. SO4 2 minus do not losing their identities as they are forming more salt, which is a light green crystals. It is a crystal formed in water. It gives their aqueous solutions behavior, and they are distinctly seeing that Fe2 plus is there, NH4 minus is there, SO4 2 minus there. So that double salts are simply the molecular addition compounds, depending that the ions in aqueous solution do not lose their identity. So uh, it's the double salt. In complex salt, it's opposite. In ions in aqueous solutions may lose their identity. So first, I am giving an example on this that how double salt and complex salt they are losing their identity. So uh, type of complex salts. First, I am classifying the complex salt. Salts are two type: perfect complex salt, imperfect complex salt. Okay, but uh, according to JU, these complex salts or double salts are mainly come in the types of reaction chapter where we do that. How can we write reactions? How can we write reaction without memorizing? That we can do any reaction without any memorizing or making notes that these reactions will do these reactions. We can do any reaction by some sort of concepts and by some sort of learning. So in on that chapter, we are mainly focused on complex salts and double salts, how they are KSP based, their degree of ionization. But in coordination chapter, we started with that classification of complex salts in four types: complexes having simple cation and complex anion. These are some PDFs that I have taken. So you can see that uh, classification of complex salts. Classification of complex salts. Uh, drawing is complexes having simple cation and complex anion. Complexes having complex cation and simple anion. So in first classification, complexes having simple cation and complex anion, we are seeing that potassium silver cyanide, potassium, this is ferric cyanide complex, and in complexes having complex cation and simple anion, uh, here anion is simple, but the cation part is complex. In the first side, cation is simple, but the complex side, the complex anion is that anion is complex. You're seeing that whole things that in anion side are having a coordination sphere. So you can see that first I have to complexes and both cation and anion complex. Here both cation and anion complex in neutral or molecular complexes, uh, carbonyl complex, neutral metal carbonyl complex. It's a carbonyl complex are neutral. Classification of complex solves on the basis of type of ligands on central metal atom and ion. Here we are saying that the ligands, we talk about ligands later, but first understand that this in this complex part, the CN minus is ligand and it's the same type that the iron part is being surrounded by whole 6 CN minus. And here we are saying also that NH3 minus is surrounding, which is 2. No any other ligand is there present. Here aqua, that water is present surrounding the cobalt part, cobalt 2 plus. So in cobalt 2 plus, that we are seeing that cobalt 2 plus is center and H2 6 H2O, which is a ligand, neutral ligand, is surrounding whole uh, cobalt 2 plus, which is the same time, means same ligand is there. So it is homoelectric complex. Heteroelectric complex is thing that metal surrounds by different type of ligands. Okay, so here, how can we represent a complex anion? Okay, how can we represent a complex anion? This is metal, any metal having some charges, and it is a ligand. Okay, surrounding the metal, central metal atom, yeah, ion, and central metal atom ion usually d block cation. Why d block cations? Because in d block cell, how many d orbitals are there? 5 d orbitals, and one d orbital they can accommodate 2 electrons. So mainly d orbitals are taking. Why? Because in coordination sphere we're mainly discussing 6 coordination number, 4 coordination number, 5 coordination number. So they are have so to deal with the electrons that they are giving to the metal atom, metal cation. So they have to be a valence cell. So d block have 5 in d block. We have seen that 5d orbitals are there. So ligands can actually easily give their electrons to and can coordinate with the metal atom or metal cation. Surrounding ligands are Lewis based. Ligands are generally Lewis based, and X represent the total number of surrounding ligands, and there is a charge. We are seeing that the charge, unit charge on a coordination sphere. And apart from this is a coordination sphere, and apart from the coordination is an ionization sphere outside the coordination sphere. Okay, and electron is species which can unite one or more electron pairs with the vacant orbitals of central metal atom ion. Classification of ligands are on the basis of charges, on the basis of density, on the basis of electron pair donating and accepting tendency. Here, on the charges, we have negative ligands, neutral ligands, and positive ligands. On the basis of density, we have monodentate, polydentate ligands, and ambidentate ligands. Now, on the basis of electron density, accepting tendency, see classical normal ligands or non-classical ligands. So, first, I'm seeing that any. I'm finding one file that I can show better from there. Okay, good problem. Negative ligands carry negative charge. Hydride, fluoride, if we are seeing examples, their whole negative ligands are carrying charges. O2 minus peroxide, superoxide, oxide, cyanate, thiocyanate. Yeah, all on a basis of charges we have classified. Neutral ligands are also there. Amine, aqua. We are seeing a carbonyl ligand, nitrosyl, dioxygen, dinitrogen, and pyridine, benzene, organic ligands, normal ether, thioether, methylamine, triphenylphosphine, hydrogen in positive ligands carrying positive charges. As they are generally, we are just seeing that in many complexes, in coordination sphere, we find that positive ligands are rarely seen, that it's less. We see only most of times negative charges, ligands, and the neutral ligand only. So going forward, density is what? Ligand की density क्या है? What is the density of ligand? Density of ligand represents number of coordinate bonds that it can form simultaneously to the same central metal atom या ion. Monodentate, polydentate. एक डेंटिसिटी को ऐसा समझो कि कोई सेंट्रल मेटल एटम या आयन है, साइमल्टेनियसली कितने कोऑर्डिनेट बॉन्ड बन सकते हैं? हाउ कैन वन कोऑर्डिनेट bond form with the central metal atom या ion? So it's shown in density. Like one ligand, if I take one ligand, hydride, so it can form only one coordinate bond with central metal atom and ion. So its density is 1. Fluoride ion, we can take example. Fluoride ion can form only one coordinate, two coordinate bond. So its density is 1. How can we know that its density is 1? Main question is arises that how can we say that chloride, bromide, iodide, or any isocyanates, amides have density 1 or density 2? First, that we know that we have to go for electronic configuration and its cell, that how can it donate electron pair? How can it form a bond? We generally see that fluoride ion give only one coordinate bond with the any central metal atom ion or any atom. Okay, we are discussing a flexidentate ligand. Among these monodentate ligands like sulfite, sulfate, nitrate, acetate, and carbonate can also act as bidentate ligands. So you are seeing this slides where you are seeing that examples of flexidentate ligand is carbonate, acetate, nitrate, sulfite, sulfate, and polydentate ligands example. Such ligands are capable of donating two or more electron pair to the same central metal atom ion through coordinate bond. While doing so, they form 5 to 6 membered stable ring. Hence, such ligands are called chelating ligands. Okay. That main thing that I want to discuss, that mainly question arises that having 5 to 6 membered ring, how can one whole structure be stable? It's of two reasons. It's of entropy side, and while seeing by entropy, we are seeing that they are being more stable, and by seeing from another side, we can see from strain. In 5 member ring, they are facing less strain and less angle strain and forming stable ring structure. So in bidentate ligands having two donor atoms, we are seeing that in oxalate we have two oxygen minus atom which are coordinating with metal atom. It's a symmetrical ligand. How it's symmetrical? We can pass a plane of symmetry. We can pass a plane of symmetry that it can bisect the oxalate. In ethylene diamine, it's also symmetrical. Symmetrical कैसे? मैंने एक plane pass किया. It divided whole compound into parts which are equally apart. So ethylene diamine is also symmetrical ligand. Dipyridine, symmetrical ligand. Phenantholene, symmetrical. There are some examples. And butylene diamine also symmetrical ligand. Propylene diamine, which are also symmetrical ligand. Okay. And I want to give one example of nickel chloride. nickel chloride react with dimethyl glyoxamate and also the structure of dimethyl glyoxamate to form oxidate PPT. Where we are taking two, we are balancing. It's a PPT. So it's oxidate PPT, let's oxidate. So first, uh, again, I am showing this. Yes, we are seeing that nickel chloride plus 2 dimethyl glyoxymeto giving oxidate PPT. Here we are seeing the structure. Here in dimethyl glyoximate, it's a ligand. So do not say it's a both nitrogen atoms rather than oxygen atom. Why? One question can come from this side. One nitrogen atom beca- because in this case it's get extra stability due to the additional stable rings through hydrogen bond. As we are seeing that in this bis dimethyl dioxymetal nickel 2, number of formed rings is 4 and 2 rings are 5 member and 2 rings is 6 member. While going that if we go through oxygen atom, then we get one big member ring. But due to the not getting stability from hydrogen bonding, the nature accepts that it's accepts if we find from spectroscopy that base methyl oxymetal has having 2 rings which is 5 membered and 2 rings is 6 membered. It gets extra stability formation of hydrogen bonding. Okay, we have discussed symmetrical and unsymmetrical ligands and types of polyhedral ligand we can see diethyl tetraene diene, triethylene tetramine, tetraethylene pentamine, and okay. In tridentate ligand, we have diethyl tetramine, tetradentate ligand, pentadentate ligand, hexadentate ligand. While discussing hexadentate ligand, we have one main compound that from one question can come and asking about the bond angles, about the denticity depending upon the pH in solution. So it's a flexidated behavior. It can act at different pH, at different denticity. It can show. Here we are seeing that ethylene diamond tetraacetate having can have 6 denticity and also 2 denticity depending upon the pH of the solution. As pH of the solution decreases, the denticity also decreases as they have hydrogen bonds. So while increasing the pH, we are getting more denticity due to that hydrogen bond can react with OH minus or some base there due to which its pH is high of solution. So it can react and can form an anionic ligand whose denticity is more. Here we are seeing it's important geometry you can see and you can also understand that how that calcium ethylene diamond tetraacetate are forming a structure where ethylene diamond tetraacetate is coordinated with calcium 2 plus cation, and this compound is having great application while going for research that you will see that this compound in application part of the combination compound is being used and while to get analyzing the uh, percentage in milk. We are using this also and embedded ligands. When negative ligands have at least 2 donor sites, but at the time of coordination, one donor site is used called embedded ligands with monodentate behavior. However, embedded ligands having sp2 or sp3 hybridized central atom can also act as fascinated ligand. Okay. As you're seeing the bipyridine, ethylene diamond, oxalate, there are some ligands, and tridentate ligands, tetradentate ligands, coordination compounds and complexes. Here you can see a more better visualization that it's central metal. The whole ligands are surrounding and coordination compounds sphere, and the possible geometries it can have coordination number 2, coordination number 3, coordination number 4, coordination number 5, coordination number 6, and also coordination number 8 can also be possible, but we are not discussing this coordination number 8, we are discussing till coordination number 6. Okay. But 6 is very common coordination number, and coordination number is nothing but it is total number of ligands attached to the central metal atom through the coordinate bond. Okay, we are discussing by Werner's theory. As Alfred Werner developed a model of coordination complexes which explains the following observations. Cobalt 3 Cl3 6 NH3, cobalt 3 Cl3 5 NH3, and they're doing some experiment with first he take a cobalt 2 plus chloride and reacting with ammonia in presence of air. They are getting a complex compound having different colors and while reacting with silver chloride. While reacting with aqueous silver, you are getting a different PPT. It 3 silver chloride PPT, 2 silver chloride ions are giving 1 silver chloride. So they are checking the conductivity, how silver plus cation react, and as we know, silver chloride is a PPT form and is white in color, as we know it. So while reacting with the complexes having different coordination spheres and having different colors, they are getting that having different conductivity and different ions having different modulation formula unit. So he, by this experiment, by Wunder's theory, uh, he postulates something that central metal atom in the coordination complex has maybe two types of valencies: primary valency, which is ionizable and non-directional; secondary valency is non-ionizable and directional towards the phase position space. Every metal has a phase number. Okay. So the charge of complex, coordination number, coordination sphere, center metal atom is seeing uh, oxygenator in state, which is 3 in this complex. And by discussing oxidation number as we have studied in physical chemistry or in it is the charge we're discussing redox. It is the charge which central metal atom appears to have if all ligands are removed along with electron pairs. It is shared with central atom. Knowing the charge on a metal complex ion and charge on each ligand, one can determine the oxidation number for the central metal atom and ion. Knowing the oxidation number on the central metal atom and the charges on the ligands, one can calculate the charge on the complex ion. So we can, these are the examples you can practice. And okay. And okay, we are seeing ambit when negative ambidextrous ligands examples we will see when negative ligands have at least two different donor sites. But at a time of coordination, only one donor site is used, are called ambidentate ligands with monodentate behavior. Why monodentate behavior? They are at the time of coordination, only one donor site is being used. However, ambidentate ligands having sp2 or sp3 hybridized central atom can also act as fractionated ligands. We will see that how it's shown fractionated ligands. So we are seeing that thiocyanate S coordinating with metal atom. So this ambidentate ligand some monodentate behavior as it can have thiocyanate N and thiocyanate S. As they have two different donor sites, sulfur and nitrogen. But at the time of coordination, only one donor site is being using. So it's an ambidentate ligand. Cyanate isocyanate example. Cyanate isocyanate is example. Nitrite, nitrite O can also act as fractionated ligands as they are nonlinear. Sulfide, thionitrides, thiosulfate O. At the time of coordination, if we see that thiosulfate S, so only sulfur at the time of his coordinating. Thiosulfate O is means that oxygen is coordinating. Sulfide S means sulfur is one who is coordinating with the metal atom and giving a lone pair. Okay, we have discussed on the basis of charges, on the basis of denticity, and we discussed on the basis of their electron accepting tendency, giving tendency in terms of lone pair and pi electron acceptor or giver. Classical, we have classified into two: classical and non-classical. Classical is normal ligand, non-classical is pi acid ligand. Okay, and classical ligand and non-classical ligand. Classical ligand, like we have hydride OH minus, that when any metal is there and they are giving a electron with the help of sigma orbital, means that they can coordinate their lone pair through vacant orbital through coordinate bond. And this is it's a sigma bond, sigma coordinate bond. So ligands donate their lone pair to the vacant orbital of central metal atom, and area singlet opposite. The ligands can donate their lone pair to the vacant orbital of central metal atom ion to coordinate bond. After classical normal ligand, types of complexes on the basis of metal ligand interaction, sigma bonded complex compound having metal donation through ligand interaction, sigma and pi bonded complex compound having a metal ligand interaction with sigma donation pi acceptance, and pi donation bond compounds. Okay. Non-classical ligands, when ligands donate the lone pair to vacant orbital of central metal atom या ion and simultaneously accept lone pair from filled d orbital of central metal atom ion through back bond, either into vacant atomic orbitals. Definition of space study. Here, through sigma pi and accepting by pi. Means in non-classical ligands, when ligands do not their lone pair to the vacant orbital of central metal atom या ion and simultaneously accept electron pair from filled d orbital of central metal atom or ion through back bond. एक सेंट्रल मेटल एटम आयन है. अब वो एक नॉन क्लासिकल लिगेंड्स में क्या होता है कि सेंट्रल मेटल एटम आयन है हमारे पास है, लिगेंड्स अपने लोन पे डोनेट कर रहे हैं थ्रू सिग्मा बॉन्ड टू द वैकेंट ऑर्बिटल. साइमल्टेनियसली वो इलेक्ट्रॉन पे एक्सेप्ट कर रहे हैं क्योंकि सेंट्रल मेटल एटम या आयन के पास डी ऑर्बिटल्स है, वो डी ऑर्बिटल से इलेक्ट्रॉन पे एक्सेप्ट कर रहे हैं थ्रू बैक बॉन्ड, आइदर किसमें वैकेंट ऑर्बिटल में दोनों एटम के या फिर पाई स्टार मॉलिक्यूलर ऑर्बिटल के लिगेंड के. मॉलिक्यूलर ऑर्बिटल थ्योरी में हम लोग डील विद पाई स्टार और सो पाई. अब लिगेंड्स के पाई स्टार मॉलिक्यूलर ऑर्बिटल ऑफ लिगेंड में जो सेंट्रल मेटल एटम आयंस के जो डी ऑर्बिटल्स है, फुल फिल्ड डी ऑर्बिटल्स है, वो एक्सेप्ट कर रहे हैं थ्रू pi back bond in either in vacant orbital of donor atom or into the pi star molecular orbital of ligand. Here we have to ligand can coordinate with metal atom through sigma or pi. So there are two categories here. We are seeing carbonyl compound, nitrosyl compound, nitrogen, triphenyl phosphine. They are coordinating with ligand with sigma bond. Here we are having pi ethene, pi benzene, pi allyl, pi butadiene. They are coordinating with pi bond. And organometallic complexes are type of complexes compounds with metal carbon linkage. Metal where M is mostly metal and maybe non-metal or metallide with less electronegative value of the than the carbon, and carbon atom is of alkyl aryl group including CO. Ammonium group cation can never act as a ligand. Why? Because ammonium cation cannot act as a ligand because they don't have lone pair to coordinate with metal atom. Metal cation with more than 2+ oxidation states usually have a stable coordination number 6 with any ligands. And there are important points regarding ligands. You can see that, and you can understand this that monodense ligands having more than one lone pair of donor atom can act as bridging ligands except carbonyl, which can act as br- bridge ligand with equal sharing of electron of carbon. Neutral ligands in which two different atoms are having lone pairs like CO and O. The preferably donor side having less electronegativity atom due क्योंकि जो ज्यादा इलेक्ट्रोनेगेटिविटी एटम होंगे वो लेस प्रेफरेंस देंगे टू गिव इलेक्ट्रॉन टू गिव अवे द इलेक्ट्रॉन्स टू द सेंट्रल मेटल एटम जो लेस इलेक्ट्रोनेगेटिविटी वैल्यू है जैसे सीओ में लेस इलेक्ट्रोनेगेटिव एटम कौन है कार्बन है कार्बन विल गिव इट्स इलेक्ट्रॉन this is carbon and carbon will having lone pair if we donate to any metal. Okay, this is a coordination number. Total number of electrons pairs accepted by central metal atom from the donor atom of surrounding ligand is called coordination number of central metal atom ion. It is also called secondary valency of central metal atom ion by scientist Werner. This is a table, and you can see the table how you can observe that having charge on central metal atom greater than 2, 3 plus, which is 4 plus and 3 plus, most of have coordination number 6, except silver 3 plus and gold 3 plus. We will discuss why silver and gold having oxygen state plus 3 have coordination number 4 and always act as a square planar. If we can I will tell to you this thing later on studying crystal field theory or valence bond theory, and these are some examples. Okay, we will discuss synergy bonding also in metal carbonyl complex. Okay, so okay, synergic bonding. How experimental evidence of synergic bonding metal carbonyl complexes by IR spectroscopy. See that this is metal and having negative charge, positive charge, or zero charge. Okay, and this is negative. We having d orbital doing back acceptance by pi bond to the molecular orbital of CO. CO having big sigma donation. By infrared rays, we will see that CO bond order is less than 3 and metal to ligand bond order is greater than 1 due to having pi backbone and weak sigma bond. Both are there, due to which its metal to ligand bond order is greater than 1. So there is a stretching frequency of CO bond, energy required to stretch CO bond, and we have formula that we have studied like harmonic oscillation in physics, 1/2 pi c under root k by mu. Okay, 1 second, wait, I am coming. 1 second. Okay. The wave numbers formula is 1/2 pi c under root k by mu, where mu CO is stretching frequency of CO ligand, energy required to stretch CO bond, C is velocity of light, force constant of CO ligand, reduced mass of CO ligand, strength of back bond is proportional to negative charge on metal cation. We will see after that why strength of back bond is proportional to negative charge on metal atom, and why strength of back bond is proportional to CO bond length of inversely proportional to the bond energy. Also, strength of back bond is proportional to the metal ligand bond strength energy, inversely proportional to bond metal bond length. These are some exercises, and we will also see effective atomic number in next time. Total number of electrons present on central metal atom ion after accepting electron pairs from surrounding ligands is called effective atomic number. There's one formula: effective atomic number for atomic number of central metal atom minus oxygen state of metal atom ion plus 2 times the coordination number of central metal atom and ion. And there's some violation of Sidgwick rule, where Sidgwick rule of effective atomic number said that according to this rule, when effective atomic number of central metal atom or ion in complex compound is equal to nearest noble gas configuration, and the stability of such complex is more. Here, sandwich compound is also there. If more than one pi electron pairs are involved in coordination in pi complexes with central metal atom ion, its coordination number is not defined. We will discuss the whole thing later. How that valuation is there, how can we calculate effective atomic number of coming to the nearest number gas configuration followed by the Sidgwick rules of effective atomic number.